Hey, how's it going, everybody? It's Liv, and today I'm just going to show you the one very effective way that I've found called C code from Perl. All right. So I believe I've shown little bits of this before, but just for completion's sake, we're going to be looking at one of the bindings that I'm creating here. So okay, I have this project over here. It's written in C, mostly in C, and it's a little bit of a keyboard driver, if you will. Let me just compile it real quick. Okay, so it's fine. Let me just run it, and yeah, it's just this, right? So you have the clock in here to the left, and you see you have like I can write, I think. Oh no, that's disabled now. But yeah, actually I can just make that modification real quick. Just RDTI or RTI or PSI. Let me see. PTI. All right. Okay, so let me recompile that. And there we go. Now if I try to run it again, I can just move around and just write. Okay. So this is effectively a keyboard controller. Right, so it's a fairly low level implementation, and it's actually pretty fast. Now what I want to do is I want to call this exact same code, I want to call it from Perl. Okay, so there's a few details, a few intricacies of the implementation which I'm not going to go into because it would take me a while. What you need to know is that this system requires these two files, this keymap1, which is also being generated, right? So this is basically the keys that are in use by a particular application, right? So this one is being generated for the C version, which is more of a demo at this point, because I'm not really using it directly. Then it needs the key calls, and this one is also generated, and this is just a collection of callbacks, right? So callbacks that are attached to a particular key event. As you can see, we track tap, hell, and also release. So when you press the key initially, when you keep it pressed down, and when you let go, those we recognize those three events. Just entirely in C, no SDL or anything. So it's actually, no extra bloat there in the middle. And then we also have additional functions for the text input. That's what this TI is for. So anyhow, this is not very complex code to write. It's just boilerplate, and that's why it's being generated from a file. Now, if you take a look at this library file in here, this one is also being generated. And what is in here, this is a bunch of bindings to a lot of the functions that make this system possible, right? So basically the guts of the system is being exported as a automatically generated FFI binding, right? Utilizing FFI Platypus, of course. It doesn't say so here, but it's using FFI Platypus. But what about the source version of this? It's a dummy. The real one is generated. And what we do is we just extend the functionality of this. For instance, here we have some subroutines for handling the keyboard and things. And it's just it's also mostly boilerplate, but this one is one that I wasn't so comfortable generating because I need some actual logic in here. So yeah, but for the most part, the way it works is pretty straightforward. I have a little demo in here of this. So, lots of imports, yes, because we want to utilize the clock. The CTL, it's for control, so this is basically when you want to pass control of a keyboard to different modules, and each module uses different keys, right? So you have to register each one of those individually. DPY is just for a couple of cleaning and restoring the display functions. Keyboard is just the keyboard, and loop is it's a driver for the main loop, right? So it's something like this, right? So this is basically the main loop for this for most of Lycon applications. You just run the clock, you draw if you have anything to draw, right? Then you just tick the clock and you just check for events and run a logic loop, right? And of course we have a panic timer, because if I mess up the math anywhere, you know, we won't just be stuck, because of the way I have to take control of the keyboard, right? So the way that the C code takes control of the keyboard, it disables it disables signals, right? So Control C will no longer terminate the running of the program. So anyhow, this one is a little bit of a lengthy demo for opening up a file and reading it in the console. I'm not going to go over the details of the implementation, but you know, it's mostly you say, okay, so I have this thing we call key set, right? So for instance, exit maps to the escape, right? So here I'm just setting a variable, and then this variable is checked when running the loop. Is the value of this terminate variable is checked, and if it's set, it just exits the program. Then for move A, that's for the arrow keys, right? And so we just have a callback for when the key is pressed, and the same callback for when it's held down. Fairly simple. And yeah, there's not much else to it relating to the configuration. Now, you might look at this and you might say, it's a little bit complicated, you know. But yeah, we are still in the process of simplifying the interface side of things. The important thing here is that we can take a Perl subroutine, convert it into a closure. I think it's the terminology that's in use by the FI guys. We convert a Perl subroutine into a closure that is a subroutine that can be called from C. And because our system is designed to attach callbacks to keys, we can just assign these, no problem. So basically, these functions will be called from C. Then we just set the logic function, and you know, this is the logic step of the program. It's just printing things to screen, and here we're just enabling the configuration, the keyboard configuration for this particular module, and running the loop. Okay, so let's just take a quick look at what that looks like. It's just going to open up and read this file, which is the, again, automatically generated make script for this file, right? So lots of code generation. So anyhow, let me see, it's a test editor. Let's just run it, and as you can see, it opens up the file. We have the clock, right? And you can see it's very much giving us the same speed that we have on the other program, right? So if I just run the C binary, right, you see that this is like the speed that we get, you know. And here is, with a lot of extra work on the logic side and calling the function from Perl, we are getting very much the same speed. So as you can see, this is just incredibly fast. It might actually be the fastest way to call C code Perl. I've never seen anything quite like it. Like, I guess in Python you can do something kind of similar with C types, but it's not quite that fast. At least I don't think so. But anyhow, that's yeah, that's basically what. So how does this system work, right? How is the lichen bindings being generated, right? Because if you, I'm just going to show you again in case you did not retain that information. This module, which is what we are importing and what is giving us all of the bindings, this one is generated. The one here present in the source code is just a dummy. Just a dummy so that the building tool will not complain that the file is missing. And here is the actual one that we are importing and where all the implementation is being done. Okay, let's take a look. What I'm going to do is I'm just going to delete this. I'm just going to RAM it. And what we're going to do is I'm going to look at the at what the setup is like. Okay, so we are using Automat, which is my replacement for GNU Make. It's it's an entire re-implementation of GNU Make written in Perl, but also has these niceties with handling automatically, programmatically generated files. Okay. So how does Automat work? You have to write yourself a setup script, set the project root, right? So in here it's just this environment variable that I have. And then you have to provide some information about your module that you want to generate these auto files, right? So these auto files are generated by Automat. These are Automat setup scripts. So let me just check. Okay. So in here we are. This is the configuration settings for C, right? So this is the project where all of the keyboard stuff lives. So basically we just tell it to build an executable. It's just to exclude a certain folder from the ones that need to be scanned for files. Here's one, is just giving it a name. And here we're just saying, okay, so here is one of the files that we need to generate, right? So this is the result. And then from that result, we say these are the sources, right? So this is an executable, and from this executable, you need to create me the corresponding file, right? Likewise in here, this one is the generator, and here are additional sources. Okay. And here on the post build, all we are doing is just making outputting a Perl file, right? We're giving it a name, right? So this is the thing we just deleted. You have to give it some information. Here we're just passing it the auto name. You can modify the includes list, right? So here we are just using some of my wrappers around the Platypus amplifier. Here we have to give it either a string representing the source code of the program, or a function call that takes a given number of arguments, and the output of this function call will effectively become the body of the function. So let's call that. Let's see if I actually. Okay, we have some errors. All right, never mind. I can just run it on this side, no problem. Oh, all right. Give me a sec. So sometimes this thing acts up. I think I forgot the name of something. In a sec. It's in line wrap. And yeah. That's just that. Okay. So let's run that again. Oops. Okay. So that should be done. Yeah, just just rebuilding the build script tool. Okay, no, never mind. This part of the demonstration is not important. But yeah, and now if I go into live here, now this thing is here back again. If I remove it, try to open up again, you see it doesn't exist. And if I run the installation again, now it exists. Okay, so this is being entirely generated through Perl, right? So it's Perl outputting Perl code. So okay, let's take a look at the emitter, right? Why not? So we have a bunch of emitters, actually not that many, but yeah, okay. We have a bunch of code for emitting code. So we want to take a look at the function that is doing the binding, right? So this is should bind, that's for shadow lib bind. What is a shadow lib? It's these files, these dot files. Oops. And you know, you see this thing entirely in binary. This is actually a Perl object that has been serialized, right? And what this function does is it just opens up that file. Let me find where exactly. Oh, it's not in here. Okay, give me a sec. I think I need to find it from here, I believe. Right, so it's from here, right? So simrd. Okay, so simrd. All right, so in here, you see this one looks for within the lib folder. It looks for these shadow libs, and shadow lib just means that it's a binary file containing data about the library itself. So it's library metadata, if you will. And it starts with a dot and name of lib, right? So that's a shadow lib. Right, so it just retrieves the file as it is, and then it just concatenates all of the data that it finds, right? And it just has a list of object files. It's basically just a list of object files, you know, function names, the arguments, things of that nature. Basically the things you need in order to write a binding to a particular function, right? To a particular symbol, I should say. But anyhow. Yeah. Okay, so this thing is just getting the symbol table from right here from the getting the symbol table right here from the regenerator here. That all it does is just make sure that the shared object that we have to create in order for these bindings to work is just up to date, right? And actually, let me just show you that. You see here this liblicon.so, right? So this shared object is created specially for, you know, to be the companion, let's say, to this one Perl module. And really all it's doing is just writing this boilerplate for import and just adding your function definitions to the import, right? So on the file being on the module being imported, all of the functions will be attached. And it's important to, you know, it's key to the speed of these calls that the functions are attached, right? So they become like live X subs, which I'm not 100% on how XS works. It's too macro heavy. I have not looked too much into it, but yeah, this is as low level as Perl can go, as far as I'm aware. And so we are just attaching that. We're just generating that. And yeah, that's pretty much it. That's a wrap. So if we take a look back at the setup script, so this is the setup, right? So this generates our setup scripts. We have here this export field, right? So export, right? So export, and you see we pass it a list of headers. Actually, we could pass it a list of source files, right? But generally speaking, the convention at least is that the functions that you want to expose in a library are the ones found in the header. Okay, so generally if it's a function you want to be exposing, it's in a header, and so more or less the convention for me would be to only export headers. However, you can export a source file, right? So we could take functions from our standard.c, but that would mean, you know, picking up functions that were not supposed to be exposed, which might not be the best. But anyhow, what this thing will do is it would just look to the header file and give you a list of the definitions. And I think I actually have a demo for that, so let's, you know, I call these tests, but sometimes they're also just demos. Okay, so let me see. I think in PLPS, not quite. Okay, let me just see if I can read in the file here. Oh, that's old. That's from the we've had a lot of API changes in the last few weeks. So yeah, I'm still adjusting some things. But let me just take a quick look at this one. Let's see if I can actually run it. Let's test PLPS. Let's see. Okay, so it does give us, and it notifies us of every update, which is nice. But yeah, you see, gives us name of functions, the argument types, right? So it's name and type of argument, and then the return the return type of the function itself, right? So in here, we basically gather all of the object, all of the symbol data from the source file itself, right? And we are, in this case, as you can see, in this case, we are going through a source file itself, right? So the mechanism for scouring a file is the same. It is exactly the same. So, you know, from an implementation point of view, it doesn't matter if you give it a source file or a header, it will read it anyhow, right? So it makes no difference. But yeah, just to be nice, generally you would want to use just headers. So let's actually, you know, just for the sake of this demo, let's take a little look at this file. So we have some functions in here, and let's just, you know, just to demonstrate that this thing gets all the functions that it has to get. All right, so also it gives us the user-defined types, right? So these are the structs that are defined in here. You can see we have image in here, and it's right here. And if you don't recognize the names of the types, this is because these are the internal types that I used. Just you know, just a thing. When you write code that does these kinds of things, you get to name things your own crazy way, right? You get to name things however the heck you want. But anyhow, as you can see, word corresponds to the word size, in my case 64 bits, and so that's the size of size t in this instance, right? And so we have these 3 size t's, and these three words, right? And then we have real for float. And I think actually this should be real pointer, but I can fix that later. And same thing here for the stack. Let me just see if I can find it. Oh, here it is. Okay. So same thing again. And once again we have an array, and it isn't quite recognizing it as such. So I have to take a look into that later on, but for now no problem. So okay. Then the functions, we have del. Let's just look for it. And for some reason, the Platypus won't let me use void, which I think is utterly ridiculous. For some reason, it wasn't letting me use void. I don't remember why. I think it didn't let me use void pointers, so I had to alias it and do some magic there in the middle so that I could use something that was akin to a void pointer. It's ridiculous, but anyhow. So here you see, it takes void, gives void, and here you have it. Get bar. I'm just going to go through a couple more. Oops. Just to show that this actually works. So get bar, we take a real pointer, so that's pointer to float. Oh, actually, this is not what we take. This is what we give. Right. So returns a float pointer and takes a size t, which is the size t is a word in this case, so 64 bits. And that's exactly what we have. Okay, so you know I could just do all of them, but you probably get the idea, right? So we read through a file, we get all of the metadata of the functions, and then we just export the thing. Pretty nice, you know. Pretty nice. So yeah, let me see how long this has been going. Okay. So do we have anything else to show here? No, I think that's about what I wanted to show. So yeah, this is a pretty powerful thing, right? Because you can just take your code, any performance critical section of code, you can just take it into C, just move it there, rewrite it in C, have that performance critical area of the code handled in a compiled language, and then just create a bind. It's easier. Why loop in Perl when the same loop were written in C would sometimes be up to 64 times faster. Some people say 100 times, but I think that's exaggerating. But in some instances, yeah, but C would be 100 times faster, maybe more. Yeah, that is absolutely believable, because that's the nature of C programming. So yeah, that's basically the idea here. So just as a last thing, let me just show you. Okay, so we do have some pi. This is before the API changes, so these functions need to be moved. But you see, we do have a C2 pi subroutine here just hanging around. It's just making calls to so regenerate, which is basically the give me a symbol table function, right? And oh, what is this? It's taking up structs. And, oh, so this is. Oh, I'm going to drop the act now. This is doing the same thing that we do for Perl, but for Python, right? So yeah, I actually have this in the works. I had it in the works for a while now. I never completed it because I'm not working too much with Python nowadays. The significant white space really just makes me cringe now. But you know, Python is a useful language, and you know you can do a lot with Python, and you know a lot of programs they will give you a Python console or things like that, right? So you know it's useful to, you know, it's an, you know, just by virtue of being ubiquitous, Python is pretty good for interfacing with programs dumb enough to use it, you know, like Blender. Yeah, you know, Blender 3D. If you have Python code, you can do anything inside of Blender. So yeah, we have basically the emit Python version of the Perl code that I showed you. So we do, you know, we basically have a Python emitter. I just have to do a little migration, which I'm not too motivated to do right now because basically I don't have much use for it just yet. Well, I guess actually I do, but it's not going to come into play for a few months, so yeah, just delaying it until then. So yeah, next up, I guess we'll be looking at any other languages that we might be wanting to create bindings to. I have my mind set on Ruby. I like Ruby. I rather like Ruby. I don't know it all that well, but I guess it would be nice to offer support to Ruby as well. And I don't know, maybe Lua. I don't know Lua, but I know it's one popular option. What else? I'm trying to think of interpreted languages. I have no idea how JavaScript would do this kind of thing. I don't think JavaScript does this kind of thing. Like JavaScript is confusing to me because I always thought it was supposed to be just a browser thing, right? So, like what? You know, it's just confusing at this point. But yeah, like I suppose you can. I suppose you can, at least with Node. You probably can. There's likely a way. And oh right, WebAssembly. Right, what am I thinking? No. Then no support for JavaScript. No support for JavaScript. Yeah, right. Because for WebAssembly, you basically have to rewrite your programs. That's what. Like it's not going to compile like right out of the box. At least I don't think so. But maybe yeah. I don't know. Well, anyhow, I don't like JavaScript, so yeah, it doesn't really matter. But anyhow, that's it from me. Automating things since 1994. Okay, have a good one. Bye.